All right, here we does it work? Where are we here? Okay, seems like working. Yeah. Okay, welcome to the fourth lecture, third week. And it's the second part on linear differential algebraic equations with constant coefficients. Constant coefficients, that's important. Today we talk about regularity, and then we will introduce the Weierstrass canonical form, which is the, so to say, the special case of the Kronecker canonical form. I hope you all remember this huge matrix that I wrote down last week. So there was this Kronecker canonical form, and if the system is regular, then all these then the non-square blocks of this Kronecker canonical form, they vanish. And then we get to the Weierstrass canonical form, and there we finally see why this canonical form is so nice, because we can more or less directly read off solvability issues. I somehow forgot to, so here this Kronecker form was EA, that this is somewhat similar to these two block matrices. So there were always block matrices here and block matrices here on the diagonal. And I didn't tell you how this translates to solvability, how you can read off solvability here. But today we will finish the lecture with looking at this Weierstrass canonical form, and then it becomes pretty clear how this is related. Also, we have the exercise this week, and there I would write down how this is related. What else did we have last lecture? There was this equivalence of like E1, is strongly equivalent to E2, A2 if there was PQ such that, what was it, E2 is P E1 Q, and the same for A2, P A1 Q, so that they're related like this. And it was important that the P and Q were regular, so invertible. Okay, that we had last week. E2 A2 similar to EA1 A1, and then with this similarity transform we could derive these Kronecker canonical form. Now we will add regularity of such a matrix pair, and then we will get to the Weierstrass canonical form, and then we will start talking about solvability. And solvability, if you think of like systems of equations, what somehow is like the natural thing, unless you do something weird with projections and whatever, that you have as much unknowns. So this is the number of equations, this is the number of unknowns, and you want to have them the same. So this means same number of unknowns and equations. This is, so to say, the regular case, and this makes a lot of sense. Also, if we talk of differential algebraic equations, you want to have as much unknowns as you have equations, and the other way around. And this in particular now means that E and A, as they we don't use this sign, as they were describing this DAE Ex dot as AX plus F. Now we want to have them E, A, both to be square matrices. Now we stay with the complex numbers, but doesn't matter so much at this point. But what is now important, M is N, so we will consider EA to be square matrices of size N. And only for square matrices the next definition will make sense, as you will notice very soon. So definition 3.2, you want to look it up in the script. I hope I will add this night. But should be there by the end of the week. So just let me have a little look at my notes to be okay. So this is now the definition. Let's take another color. So let E and A be square matrices. Then the matrix pair EA. So take those two matrices and consider them as a pair. So the pair EA is called regular if the determinant of lambda E minus A is not the zero polynomial. Okay, so this is definition for regularity. Here we go. What we will need is this determinant of lambda E minus A. Well, that's like one plausibility check whether you can talk of regularity if you don't have a square matrix. You cannot define the determinant. And then you want that this is not a zero polynomial. Here I wrote it down. Not the zero polynomial. This basically, there are many equivalent characterizations for that, but one thing could be that there is a lambda 0 such that lambda 0 minus E, lambda 0 times E minus A is invertible. Well, and this like there is no, that's not a zero polynomial, so the determinant will give you a polynomial in the lambda, and there is one lambda such that you won't have a zero determinant here. Or another characterization as, no, actually it's the same. The determinant lambda E minus A is not zero for almost all lambda. Well, there can be at most a finite number of zeros to that. So either it's completely zero, or there's just a few numbers where it's zero, and the other way around. This means that this determinant is non-equal to zero for almost all lambda. Shall we make an example to that? Maybe a very easy one. So consider, well, so that we see some things like E being that, A being 0, 1. Okay, two things that you can see. If E is invertible, then of course the matrix pair is regular. Okay, it's easier to see if A is invertible, then you choose lambda 0, then you have a non-zero polynomial here, and here the determinant will then be determinant of lambda E minus A as then simply lambda minus lambda. And you see this is not zero for most lambda. It's only zero for lambda is equal to 0. No, somehow. Yes, it is. So that's what you get here. All right. So, and this is regularity. And next thing that we show is that this regularity is invariant under strong equivalence. So meaning that if we apply the strong equivalence to a matrix pair and we get the regular matrix, then the other matrix, the matrix pair that we started with, is regular too. And in mathematical term, in this lemma, this means that every matrix pair that is strongly equivalent to a regular matrix pair is regular. And the proof is basically a one-liner. So assume E1, okay, it's maybe it is equivalent to E2, A2 with these matrices P and Q now being square matrix and invertible. Then it holds that the determinant under E2 minus A2 as the determinant of P times lambda E1 A1 times the Q. And now that's a rule from taking determinants. This is the same as the determinant of P times the determinant of lambda E1 minus A1 times the determinant of Q. And you see, since this is non-zero, if P is invertible, then this is non-zero and this is non-zero. And so we will have that, well, if this can only be 0 all the time if this is 0 all the time. So other color here, that's the one we just had. So this can be 0 all the time if and only if this is 0 all the time. Okay, and that's why regularity is invariant under this equivalent transformations, and that's why it's also a useful concept in what we consider, because as I said, so it makes a lot of sense to consider strong equivalence of matrix pairs, because this means operations that one would do on a system, like scaling the equations or changing the state space, since regularity is works well together with the strong equivalence. That's why how this all fits nicely together. And why this is another nice thing for DAEs, we will show that this DAE EAX dot plus F is solvability is solvable up to some strange cases, but in general it's solvable if this matrix pair E and A is regular. So for regular matrix pairs, it makes sense to to investigate solvability in a very general case. Of course, there are always some specially constructed cases where things look different, but the general case of solvability requires that this EA is regular. And in particular, we will show that if EA is regular plus F sufficiently smooth, then EX dot plus SAX plus F of T has a solution. So it's solvable, it has a solution, as we had it in the definition for solutions. So this thing here And second, we will show also x0 is consistent, then the initial value problem has a unique solution. Unique solution. Okay. Well, and we start with this one and sufficient. Well, actually, we will show that if this is not the case, then well, so there's an if and only if. But for now, we start with first thing will be showing this sufficiency, namely that E and A is a regular matrix pair, and we want to consider this DAE. Ex dot is AX plus F. Well, then we know EA is regular, then this will have a solution. And then we can also go and characterize consistency of the initial value and so on. And also we will see under which circumstances it also holds that this can only have a solution if this pair is regular. Okay, but let's start with the sufficiency. EA regular, then we will find a problem, a solution to this problem. And the working horse for that is the Weierstrass. Weierstrass canonical form. Which is the Kronecker canonical form for regular EA matrix space. This is this theorem. Let me just have a quick look and what this looks like. Okay. So here goes the theorem. That as above, E and A be square matrices and regular. Then it holds that this pair EA is strongly equivalent to a matrix pair that looks like that. So here's an identity matrix. Here is an N matrix. We will talk about that. There's zeros on the off diagonals. Or this is blocks, and well, others than that there are zeros. And this A matrix is transferred into a J matrix, which will be Jordan canonical form matrix, and an identity here. Okay, so EA regular matrix pair, then it is equivalent to the matrix pair in this form, identity N and Jordan block identity, where J and are in Jordan canonical form, and where N is nilpotent. Two things. See, I have prepared this. I will tell you about this Jordan canonical form and nilpotency in a second. But let me still make this remark. Moreover, the one or the other block may not be present. So it may happen that either these first block here, the IJ part, will not be present. So if you haven't, we will see this, if you have just an ODE, then this block will not be there. But it may also happen that this block is not there, then this Weierstrass canonical form has only this N block and the identity. Okay, that's the theorem, and we will even prove this on the next slides. But first, let me tell you what means Jordan canonical form. This means that such an M and general M and as a square matrix is always similar. We will talk about the similarity. It will be always similar to a J matrix that looks like J1 to some Jm, where the Ji are these Jordan blocks. Actually, yes, lambda I, lambda I, and ones on the above diagonal. So these typical are the Jordan blocks. That is, and importantly, the similarity means similarity for matrices. Similarity for matrices. I hope you all recall how similarity for matrices is defined. Actually, okay. M1 similar to M2 if and only if M1 is T, M2 T to the minus 1, where T is a invertible matrix. So that's how a similarity for matrices is defined, and it's you all had this in linear algebra, that every square matrix is similar to every square matrix has a Jordan form in the sense that it's similar to a matrix of this type. And these lambda I are the eigenvalues of this matrix, and they can be 0 in particular. Okay, and this brings us to nilpotent matrices. If they are 0, then this Jordan block is called nilpotent, and nilpotent is so N is nilpotent if there is a new natural number such that, let me look this up again to have such that n to the new is 0 and n to the new minus 1 is not 0. So n is a square matrix, you can multiply, you can square it, you can put it in the third power, and there will be one power when this is 0, but importantly there is a so if it's in a new power it will be 0, it should be not be 0 in the power before. This is needed to have this index, this nilpotency index well defined. An example would be, for example, the matrix 0, 0, 1, 0, which is obviously not 0, but if we like 0, 0, 1 times a 0, 0, 1 matrix, 0, 0, 0, then this is 0. This is the 0 matrix. Okay, and also nilpotency, nil means 0 in English too, and potent, so there's a certain exponent for which this will be 0. Okay, and now we want to do the proof of that, and we want to prove that for any EA being square regular regular matrix pair, we can find transformations so that they are similar to EA in this form. This will be the proof. Here I made a little mistake when preparing. Well, I think I can cut this in in the post-processing. But well, we want to prove, actually what we want to prove, we want to prove there exists PQ invertible such that, I write it like this, lambda e minus a multiplied with p from this side and q from this side will be lambda identity n minus j identity. Okay, that we want to prove. We want to find p and q matrices such that if we multiply this pencil lambda e minus a from the left and the right, then this will look like lambda in and minus ji. Yeah. Recording is running. Okay, yes. So first thing what we use is EA regular. First item of the proof, we need this assumption that it's regular. So yeah, you already see that if it's not regular, then we will have other problems. So, but if EA is regular, this means there exists a lambda 0 such that lambda 0 e minus a. Let me write this the other way around because we will use it the other way around. A minus lambda 0 e is invertible. Okay. Well, regularity, we had the definition slightly different, but it's just multiply by -1, and this will not change invertibility of such a matrix. So I hope you can agree that there is this lambda 0 such that this is invertible, and this gives us like the first similarity transformation that we do, or actually the first one is just introducing a 0 here. So this was EA, and then of course we can add minus lambda 0 plus E, and then we subtract this part again. So nothing has changed here. So of course this is similar, strongly equivalent, but in fact it's equal. And now there comes a real transformation to that. Now we apply a first P from the left, namely this one will be, so to say, P1 to the -1, which we apply here from the left. And this gives us this part, and then we see that, so here if we apply a minus lambda 0 to that part, we will get this identity here, and yeah, and well, this lambda 0 can go through that, and that's what we have there. Okay, so I hope you can all agree that certainly EA is similar to, well, to this matrix pair. Then next thing is next we want, so this is, so to say, the new E, and we want to transform a minus lambda 0 E, that's an 8 to the -1 E to Jordan canonical form, and as I just said, Jordan canonical form is, it's there for every matrix, meaning, well, there will be a regular matrix applied from the left and one from the right, and then we will have, with that we have that A minus lambda 0 E to the -1 E is in fact similar to, here is J1 to to some jk whatsoever, and then we have some more Jordan blocks. I will talk about that in a second. K plus 1, it doesn't matter so much. And M, where Ji belongs to the Jordan block, to the eigenvalues lambda I, which are not 0, and these Ni are dead blocks. I should be more careful with the similarity sign, but whatsoever. No, sorry. So not overuse this similarity sign. So this Ji is defined through the lambda I, through the eigenvalues that are non-zero, and Ni are those Jordan blocks for which the lambda I is in fact 0. Meaning, well, so these Ni, they will look like, maybe like that, 0, 0, 1. This would be one such block, or maybe one of size 1, size 2, and well, you name it. But now these blocks are all Jordan canonical form. So this is the Jordan canonical form of this A lambda 0, e to the minus 1 e. And what we do is like collecting all the 0 blocks. They will be collected in here. And the non-zero blocks, those we collect in here. And since, well, okay, no, nothing not too much to convince you here, but well, this matrix is similar to its Jordan canonic form, and with these conventions I was introducing here, we can write this as this J block and this N block. And so we assume that here there was some t from this side and some t to the minus 1 from that side, and of course we can like apply this here from both sides. So we can apply the t here, the t to the minus 1 here. Then this will give us this part here, so t, this part, t to the minus 1. That's exactly what we did here. So this will be, the first part here will be this j tilde block and this 0 eigenvalue Jordan block. And there is this other matrix here in this pair, and there also the t and the t to the minus 1 applies. And as in particular here we will have like t to the minus 1, so the identity stays, and here we will have this lambda 0 t, then everything what was inside times the t to the minus 1, and well, what is inside is the same as it is here. Well, so we will get more or less the same here, meaning this will give us the A identity plus lambda 0, this Jordan matrix, and same here, I plus lambda 0 and tilde. Okay, and little look back what we actually want to have. We want this to be similar to identity n and Jordan block and identity. Okay, that's what we want to achieve. What we already can see, well, this j tilde is invertible, so clearly j tilde is invertible because these are all non-zero eigenvalues. So it's easy to like first invert with apply a j to the minus 1 here. This will affect then this here, but then it's easy again to turn. Here we will have this j tilde j tilde to the minus 1 I plus lambda 0 j tilde. And well, this is again a matrix. We can put this in Jordan canonical form, and since it's invertible, it will only no, doesn't matter. Even doesn't matter. So well, so with the first line, that's easy. J to the minus 1 from this side, and then making this Jordan form again. And for this side, what we will show is that we can apply identity plus lambda 0 and tilde from to the minus 1. Then this will become the identity. But what we will need to show is that what stays here, namely that this is a nilpotent matrix. And also we have first to think of whether this is invertible. But that's like the easiest step of what follows. For that, first we observe that until it looks like such a matrix, only zeros and maybe things here, so depending on the size of the blocks. But this means then that identity plus lambda 0 and tilde is invertible. Okay, can you agree? Because yeah, we at an identity we will have ones here on the main diagonal, and we only have things over the diagonal, and this means that this is invertible. What is maybe a bit more difficult to show is, okay, the next step is I plus lambda 0 and to the minus 1 is upper triangular. Do you know why? Well, I plus this is a triangular matrix, and then, well, so one can show this by hand or maybe look up some basic facts, but the group of upper triangular matrices, well, it's a group, meaning that you can apply an inverse inside this group and you will stay upper triangular. What is maybe not more difficult to show is that I plus lambda 0 and tilde to the minus 1 and tilde is strictly, so that's some more difficult to show. Upper triangular, meaning triangular plus zeros on the diagonal. Diagonal. How does one show this? Well, one can do it like that. So say we know that. Let's do it for a 3x3 matrix. So this is, we know that this matrix here is upper triangular. So this is this I plus lambda 0 and tilde to the minus 1, and we already know that this and tilde, this has zeros on the main diagonal. 0, 0, 0, and entries here. Possibly entries here. Okay, and then, well, just calculate the main diagonals. So on the first the first new entry will be the first line times the first column. This will give you a 0. Here this entry will be the second row times the second column, and like this, then these entries will hit the 0 here, so this will give you a 0, 2, and the last entry will be this line times the last column, and this will give you a 0, 2, and yeah, that you can show. Doesn't matter of the size, you will always have the zeros. Okay, so you will have zeros on the diagonal, and this in particular means that n tilde is nilpotent. Why? Why? Well, basic linear algebra fact. If you're too interested, then you can show that. But then let's collect all this, and this in particular means that e to the a is similar to identity and J matrix identity, where among others this n is defined as I plus lambda 0 and tilde to the minus 1 and tilde. And as I said, this identity comes from inverting this J matrix, and this J matrix comes from, well, computing the Jordan canonical form of this J tilde to the minus 1 I plus lambda 0 J tilde. Okay, and well, that's the proof. Okay, oh no. Alright, so done with proof. Then let's have another look at what this now means in terms of solvability. So we have that EA is regular, then it's similar to this matrix pair, meaning that if we have this EX dot AX plus F of t, that this is similar to this system. And now I write it down in all details, just so that we have it once and for all. x1 and x2 dot being equal to the transformed A. This is J times identity x1 and x2 plus, well, also f1 and f2 of t. Okay, but note that there was also state transformations involved, so well, let me write this down. So x, I always get this wrong, but should not matter too much. So here's this state transformation that qx is now x1 and x2, and we have that pf is f1 and f2. Okay, so but please believe me that actually we want to consider this DAE, but we know that we can do state and state transformations and scalings, and now have this DAE. And if we have a look at that, we see this overly nicely decoupled into one equation that reads x1 dot as j of x1 plus f1 of t, and this obviously is an ODE, which already is in Jordan canonical form, so there's already a solution formula, an easy solution formula to that. Okay, so that's actually very easy here. And the other one is an x2 dot as x2 plus f2 of t, which is a DAE of a very particular type. Very particular type, and this DAE, this will be of our interest. We will investigate this. No, maybe to repeat this once more. If EA is regular, then in theory, so it's also important in theory, because then later if we want to solve this on a computer, we should not do that. But in theory, to talk of solvability, we can assume that the system is in that form here, in this Weierstrass canonical form. Then we see that, well, the first part is just an ODE, nothing to do here, it's already in Jordan form, very easy. And now the question whether or not this is solvable, it's all hidden in here. Talking about solutions to such DAEs, this will be topic of the upcoming lectures. Alright, thank you.